In this presentation, we're going to look at digital comparators, circuits which we will be able to put in two binary numbers and ask, are those two binary numbers equal, or is one, the first binary number, greater than the second binary number? So a comparator is going to be some circuitry that is going to perform a comparison. It's going to compare two binary inputs, A and B, and it's going to be able to address the following questions. Is A equal to B, true or false? Is A greater than B, true or false? Is A less than B, true or false, etc. Actually, we only need to figure out two of these to build a circuit to do two of these, because from those two, we can get all the rest. All we need to figure out is whether have circuitry for A equal B and circuit for A is greater than B, and then from those we can figure out the rest. So A greater than or equal to B is A greater than B or A equal to B. A less than or equal to B is not A greater than B. A not equal to B is the inverse of A equal to B. And then the more difficult one, A is less than B, is not A greater than B ANDed with not A equal to B. Let's look first at a one-bit comparator. So I have a number A and a number B, and they are both single-bit numbers, and so I can write out the truth table, all the possibilities. 0, 0, 0, 1, 1, 0, 1, 1. Then I have two outputs, the equality output and the greater than output. So when A and B are both zeros, they are equal. When A and B are both ones, they're equal, and otherwise they are not equal. So the equality output is 1, 0, 0, 1. The A greater than B output is a 1 when A is a 1 and B is a 0. Otherwise, it's false that A is not greater than B. So here is the gate version of the one-bit comparator. We have two inputs, A, B. The equality output is an excluded NOR. Note the little circle on the end, excluded NOR. And the A greater than B output is A ANDed with not B, because we want A to be a high and B to be a low. So A and not B. Now we would like to move from a single bit comparator to a word comparator to compare binary numbers that consist of several bits. So now let's start with equality. That's the easy one. So to ask if two words are equal, then you just pair up the bits that are in the same position in each word. Say the ones place, the twos place, the fours place, the eights place, match up the ones place with the ones place, the twos place with the twos place, etc. And then we ask sort of individually if the bits are equal, and then all of the pairs must be equal for the words to be equal. Next, we're going to look at the greater than comparator to compare word A to word B. And let's keep it simple and work with unsigned integer. So we start off by comparing the most significant bit of word A and compare it to the most significant bit of word B. And if that is greater, if the most significant bit of A is greater than the most significant bit of B, then A is greater. If it's less than, if A, the most significant bit of A is less than the most significant bit of B, then A is less than word B. And if the two most significant bits are equal, then we must go down to the next most significant bit and make that comparison. So if the most significant bits are equal, one compares the next most significant bits. Say one goes from the eighths place to the fours place. If the next most significant bits are equal, then one goes to the next most significant bits, down to the twos place, and so on. It might sound like one needs to know the outcome of the first test to move on to the second test, and the second test to move on to the third test, and so on, but that's not the case. So let's look at a 4-bit comparator where we're comparing a 4-bit word A to a 4-bit word B, where we are thinking of them as unsigned numbers. So A3 is the eighths place, A2 the fourths place, and so on. we are comparing the A3 to B3, the 8th place of A to the 8th place of B, in that little box that says compare is the 2-bit comparator. And so the upper line corresponds to true or false, A3 equals B3, and the lower input coming out of the compare box is whether A3 is greater than B3. And then we do that for A2 and B2, A1 and B1, A0 and B0. And we want two results. We want to know if the 4-bit word A is equal to the 4-bit word B, and if the 4-bit word A is greater than the 4-bit word B. Well, there's one way for the word A to equal the word B, and that's for all of the single bit equality comparisons to be true, and so that's an AND gate. So we AND, is A3 equal to B3, and is A2 equal to B2, and so on. Now let's look at greater than. There are 4 scenarios under which word A can be greater than word B. The first one is that the comparison of A3 to B3, that A3 was greater. The second scenario is that A3 and B3 were equal and A2 was bigger than B2. The next scenario is if A3 and B3 were equal, and A2 and B2 were equal, and A1 was bigger than B1. And our final scenario is when A3 and B3 are equal, A2 and B2 are equal, A1 and B1 are equal, and then A0 is greater than B0. And so we are taking all these scenarios finally and putting them into an OR gate, and that is our output for A greater than B.